Galileo's own diagnosis seemed to be that, unlike finite sets, infinite sets just cannot be compared in terms of size. Upon reflection, it simply does not make sense to say of an infinite set that it has equally many members as another one, nor that this would not be so. One should say of infinite sets that they are infinite and leave things at that. The concepts of equal or greater size should be restricted to finite sets only. Hence, according to Galileo, the right response to his paradox would be to reject premises 1 and 2 as false or meaningless if applied to infinite sets x and y. But that is not the only possible reaction. Here is a different response. Questioning the absurdity of the conclusion. Perhaps in one sense of the term, the set of even natural numbers does not have equally many members as the set of positive natural numbers. While in a different sense, the set of even natural numbers does have equally many members as the set of positive natural numbers. The two statements might sound as if they could not both be true, but if what is meant by equally many in each of them is very different, then maybe they are not in conflict after all. In this case, the argument should really be stated like this. Focus on the first two premises and the conclusion. P1 star. If x is a proper subset of y, then x does not have equally many members as y. P2 star. If there is a pairing off between the members of x and the members of y, then x has equally many members as y. And so on. Conclusion. The set of even natural numbers does not have equally many members as the set of positive natural numbers. And the set of even natural numbers does have equally many members as the set of positive natural numbers. If there are two senses of having equally many members as in play here, then the conclusion is not actually a logical contradiction. It's like saying, that building is a bank, but it is not a bank. This might sound like a contradiction, but if it means that building is an institution in which money is kept, but it is not a slope beside the river, there is no contradiction anymore. If so, the situation really is this. As long as we are dealing with finite sets, we understand very well what it means to count its numbers of members, and from this we know what it means to say that a finite set has equally many members as another one, and so on. But now we want to extrapolate from the finite to the infinite. We want to extend our concept of size also to infinite sets. And it turns out that there is more than one way of achieving this. If we follow one path, the set of even natural numbers turns out not to have equally many members as the set of positive natural numbers. That's equality 1. But if we follow another path, the set of even natural numbers does have equally many members as the set of positive natural numbers. That's equality 2. Rather than ending up in an incoherent situation, as Galileo seemed to think, we end up with two ways of extending our concept of size from the finite to the infinite. As soon as we turn to the infinite, neither of the two ways preserves everything that we think is true about the finite. And Galileo's paradox shows that we could not preserve everything without running into a contradiction. But each of the two ways of extending our concept does preserve something that we held true about finite sets. The one concept preserves premise 1, which is now supposed to hold for all sets, whether finite or infinite. While the other concept preserves premise 2, which is now supposed to hold for all sets, whether finite or infinite. But maybe we can do better than that. Maybe we can show that one of the two concepts is in fact better than the other one. Perhaps one ought to be preferred as extrapolation of the concept of size to the infinite case. Say, one of the concepts is such that a precise, consistent, and systematic theory of size for sets can be built around it. Where the theory is enormously fruitful, in the sense that lots of theorems about size for infinite sets can be derived from it, which also throw new light on other topics in mathematics, science, and philosophy. And where the underlying concept of size is still simple and illuminating. and assume that this is all true of the one concept, but it is not true of the other, or at least not to the same extent. Then we would have good reasons for preferring the former concept over the latter. This is exactly what we find to be the case here. First of all, premise 1 star only tells us something negative about equality 1. It only tells us when it is not the case that sets are of equal size in that sense of the word. On the other hand, premise 2 star has something positive to say about equality 2. Accordingly, it is easy to strengthen premise 2 star into a definition of equal size for sets in general. For all sets x, y, x has equally, that is, equally too many members as y, if and only if there is a pairing off between the members of x and the members of y. Equivalently, one often says in this case x is equinumerous to y, or x and y are equipollent. In contrast, it is not clear at all how to state the definition of equality 1. For instance, we would not want to define x to have equally one many members as y, if and only if x is a subset of y and y is a subset of x. According to that definition, not even 1, 2 and Hannes Leitgeb, Stefan Hartmann would be equal in size. Indeed, x would have equally one many members as y, if and only if x is identical to y, which is not right. One might think perhaps equality 2 is good for telling us what is the case when two sets are of the same size, but it does not tell us much what is the case when two sets are not of the same size. Of course, by our definition of equality 2, it is clear that x does not have equally too many members as y, precisely when there is no pairing off between the members of the two sets. But that does not seem to be very informative. In particular, which of the two, x or y, is then smaller in size, if any of them? Perhaps there is no suitable notion of smaller size at all that would accompany equality 2. It turns out that we need not worry. Just define x has less too many members than y, if and only if x has equally too many members as a proper subset of y, but x does not have equally too many members as y itself. For instance, the set 1, 2 has less 2 members than the set 1, 2, 3. As the required proper subset of 1, 2, 3, one may take 1, 2 itself. On the other hand, once again, the members of 1, 2 cannot be paired off with the members of the set 1, 2, 3. For analogous reasons, the set 1, 2, 3 turns out to have less 2 members than the set of positive natural numbers, just as it should be the case. But there is more. It follows from the principles of modern set theory that the following is the case. For all sets x and y, either x has less too many members than y, or x has equally too many members as y, or y has less too many members than x. This is just like for natural numbers, m and n, where we have either m is less than n, or m is identical to n, or n is less than m. It is not clear at all how anything like that could be derived for equality 1 and a corresponding notion of less one many members on the basis of some reasonably simple definition of these terms. Finally, it is very easy now to use equality 2 in order to define what it means to call a set infinite. X is infinite too, if and only if x has equally too many members as a proper subset of x. And we can add, x is finite too, if and only if x is not infinite too. For instance, the set 1, 2 is finite. There is no pairing off between 1, 2 and any of its proper subsets. On the other hand, the truth of premise 4 in our argument from above amounts to the set of positive natural numbers being infinite, as intended. By means of this concept of same size 2, we have finally been able to define infinity for sets in a simple and illuminating manner. Infinity amounts to a kind of self-similarity property, much as with fractals in geometry. An infinite set contains something which, in terms of size, looks like itself.